Okay, so as I said, there are mainly two things left in terms of lectures. One is related to data collection and analysis, and the second one is about validation and verification. Again, it's all these things are on the simulation project workflow diagram, right? So because you have given the quiz, so you must remember this, right? So there's a step called after problem definition about conceptual model and data collection and analysis, right? And then there's arena model, and then we have validation and verification steps. So these two parts are left. I already talked about the dynamics of data collection. I'll talk a little bit more about it in general, and then we have talked about collection, but we'll touch upon analysis. The analysis part, we will be needing arena in it, so I'm just going to show you today. But I'm hoping that by the time you have this week ends, your data collection has finished, and we can actually go to arena. Okay, so we'll just talk about these things in general, and I'll show you a few slides on arena as well. But inshallah, we'll actually do it on arena inshallah next time. Okay, so input models. Input models. We are talking about, when we say model, we are essentially referring to distributions. Inter-arrival time distribution or service time distribution. They are the driving force of simulation model. Why? Because your output is as good as your input. What you tell arena will replicate that. So if you're giving arena something else, arena will not be able to capture whatever is going on there. So you understand the importance of input. Your model will be garbage if you have not captured the right processes, arrival processes and service processes, and it will be meaningless no matter how hard you work on your arena models. It will be useless. So the ultimate use of input data is to drive your simulation model in a way that it really replicates the reality. Okay, so what do we do? So we actually have to go there and collect data either through historical records or in real time. So what are we doing in our project? Which one of these? Historical records or in real time? Yeah, but sometimes the data is available through information systems. Like if you're modeling ER, many of that data is already available on the hospital's information system. So the data can be obtained through information systems. The advantage of that is that the amount of data would be far more than what you're trying to collect like that, right? But if the data is not available, then you're already learning how to collect that in real time in a very simple way. So eventually, the question that I discussed but gave it in the quiz as well was, what do you do with that data? So you observe the data or you collect data from the information system available, and then you do a step called fitting theoretical distribution, fitting probability distribution, which will be used in the simulation model, which will be used to do the simulation. So what are the 5 steps of input model development? Collect data, identify the right probability distribution. Now, can you name some probability distribution that you know? Normal is definitely one. Now at least 2 more. Yeah, that's beta is there, but we have talked about two distributions quite frequently. Sorry? What are the names for those? Poisson and exponential, right? So some of them. So when you say fit the data, actually what you try to do is to find what you call parameters of those distributions. So when you say normal distribution, you must know what are the parameters for normal distribution. mu and sigma. That's correct. Mean and standard deviation. So if you know the value of mean and sigma, you know the shape of the distribution. So just like this, for exponential distribution, what is the parameter? Or for Poisson? Lambda, and whether you call it lambda or mu, that's the parameter for exponential or Poisson. Okay? So mashallah, you're doing better now today. So that's what you call parameter. So if you know lambda, some people even for exponential call it lambda. So if you know that, then you'll be able to actually draw the exponential distribution shape. Okay? So and then you do something called goodness of fit test. Goodness of fit test is beyond our scope, so we will not be doing it. But goodness of fitness test is a statistical test that shows the quality of fit. Whether it's like a high quality fit or not a very high quality fit. How much trust you have in that distribution. So do you understand at least the purpose of goodness of fit test? So if you're saying that 95% of the time it will capture what is going on in reality. But 5% of the time it may deviate. So that's that kind of thing we are looking at. So everybody understand what is goodness of fit? Goodness of fit is how much confidence you have in that model. And then of course the last step is you use the fitted model into the simulation. So as I said earlier, the better the fit, the better the representation. And if you have not done this part well, then you know about this very well, right? Garbage in, garbage out. This is a very famous data related thing, that what you give to the system is what it will produce. So if you're giving in garbage, it will produce garbage only. Okay. Okay. So although we have talked already about it, but the thing that we were doing here, we were doing this. What is this thing? Planning ahead. We didn't go directly, right? I said plan, make tables, draw like some print, get some pages printed out, think, what you're collecting, what would be in column 1, what will be in column 2, right? That's called planning ahead. Begin even by, they say, sometimes you have to do some dry runs. Dry run means you don't just go there and start observing. You actually go there and do 1 or 2 times you do test runs, which means that data is not included in your analysis. Why do you do that? Because people have faced problems, even in our projects. They go there, they say we sat in a place and we were unable to see the customers properly, who somehow collected it, but we are not sure whether what we collected was correct or not, because people were going and coming, and we are sitting in a place that we can't see it well, right? Or for the service part, same thing happened, that there were difficulties in because of that difficulty and because of this difficulty, we were unable to measure things well. So practice and pre-observation session is there to calibrate yourself in the sense of where and how you're recording it. If there are any technical practical problems, you need to address that. You need to see if you're able to find right place to sit, you have the right tools ready with you or not. And of course, you need to watch for those unusual circumstances that may hinder your data collection. Okay, so one of the things that here are a few things that will help ensure that the quality of data that you collected is of appropriate level. Analyze the data as it is being collected. Check for its adequacy. What does it mean? So I'm recording the number, and let's say 5 people turned up, but I quickly wrote, and instead of 5, I wrote 50. Just sometimes these mistakes happen, right? So always do check. Have a look at it. If I recorded it properly, one person writing, maybe other is checking somehow, or see the data again and see whether there's an unusual value that I entered by mistake, right? So this is going to be critical. So as you're collecting, please make sure that you somehow are trying to you somehow try to check if you're doing it properly or not. If 2 or 3 of you are collecting data for a similar situation, like in the grocery store, there are like the regular counters, 3 regular counters. We'll assume that this is homogeneous data, homogeneous circumstances, similar situation. So you can merge them together. You can even, if you're doing it exactly in the same time slot, same location, same person, and you're doing it the next day, or the next day, where arguably it's the same situation, then you can also combine those homogeneous data sets together. Okay. Now, this is one of the things that comes out of human tendency. When you become uncomfortable because of something, you feel that it will be affecting my model. So you go there and on a grocery store, and something happened. Machine broke down. You know, sometimes you see even angry people, right? And you see that the person never leaves the counter because of whatever reason. Maybe just because something happened. It has happened to us as well, right? Something broke down and they're calling for that key thing, right? So what would you do there? You would skip that data point? I heard a yes. Yeah? No. I mean, would you enter this event in your data? That's the point we are making. Be aware of self-data censoring. That's part of the process. It happens there, isn't it? Hasn't it happened there? What you're trying to capture. So it is part of the process. So be aware of these kinds of self-data censoring. You don't do that. It is happening there. Although it's a rare extreme event, but it is an event. You need to capture whatever is going on. Okay? Have you all registered that? Whatever comes. Whatever comes. You don't say it doesn't look like this is going on here, so I take it out. No, you don't do that. Capture everything. I've seen this before that people say there were those special situations and we have thrown them out. No, it doesn't. You know those long tails in exponential? That tail is actually representing those rare extreme events. And you have thrown them out. Don't do that, okay? So it's an important point. Be aware of data censoring, especially self-data censoring. Okay? So the quantity is not observed in its entirety, danger of leaving out, for example, long process times. This is more advanced stuff, something called autocorrelation. Will not go there. Sometimes an event leads to affecting another event. So we are assuming that in most of your cases that they are independent, right? You know, a person, a cashier got upset, that may affect what comes next. Are you able to see what I'm saying? It may affect the processing time later. There may be what you call an autocorrelation, a variable affecting itself what is coming after that. But this will make your life more complicated. This is advanced stuff, so we'll not assume it, but you just need to be aware of it. What does autocorrelation means? Something that is affecting itself, like a price, oil price. There might be an autocorrelation where you can find the correlation between the current price and the previous prices. Correlation, you know the meaning of correlation, right? It represents a positive or negative relation. Positive relation means if something goes up, the other goes up. If something goes down, the other goes down. That's called positive relationship. Negative correlation means if one goes up, the other goes down. If one goes down, the other goes up. Right? So that's like, and then there are measures like correlation coefficient, etc., which are used to capture that. But so we need to be aware of that. Okay, so That's data collection. So you all have registered, the key points here. Prepare yourself, make sure you don't miss the data, sit in places where, or stand in places where you're looking at everything clearly. Okay? And then don't skip out anything that you feel unnecessary, capture everything. Okay, how odd that thing looks like to you, but you just don't throw it out. Okay. Now, the next part is a bit tricky part. Analysis of data, fitting the data. I'll talk a little bit about few things, but this is more expected at a higher level. People with a more deeper statistics background or people at a graduate level. So I'm just going to throw some terms out to you, but you should not be worried about that in terms of, the technical aspects of those things. But can we live without it in simulation? The answer is no, we still have to fit a distribution. So how do we do it? Arena again comes to us for rescuing us here. There's a tool comes with Arena which is called input analyzer. I'm going to show you. So what you do is you just give the data to Arena input analyzer, like in a CSV file or an Excel file, and the Arena will does all those things for you behind. You don't even have to look at it. And then it will suggest the best fit, the second best fit, the third best fit, and so on. So, the parameters like an exponential distribution is the best fit, so it will give you the lambda value. Plus, it will tell you, how good the model fit is and so on. So some of those things. Okay. So, but if you're not using input analyzer, you still need to know a little bit about these concepts because Arena might be giving you more than one option. So still, it's not a complete blind thing for you that Arena says so because Arena says so, so I'm using it. No, still you need to be to have more than that with you. Okay, you still need to say out of these lists, I'm picking this because I know that this is a better one because of some other consideration. Are you all following me, Bana? So first thing, before even going to whether we go to Arena or not, we need to know the nature of the process, nature of the data. What does that mean? We are dealing with quantitative data, but there is more. We are not talking about that. Something on M. Do you remember MM1? It's what was M? Means what? Markovian, Poisson, exponential. There was a nature we discussed behind that. They are the arrival. All of these are random. Despite being random, they follow certain shape like normal or exponential. The arrivals are they are discrete, of course, but one arrival is that's the nature. You understand? Nature means what? Independent nature means it has to be. If it is a discrete number, then a very good contender for a distribution is Poisson. You know that already, right? So Arena might put it at number 2 because Arena has 1,000, 5,000 kinds of distributions. Some may fit, show a better fit, not because of nature, but because you have not collected enough data. So there's something called a limit to a process, which means that if you collect 5 data points and you fit, you'll see a very strange distribution. But if you collect 50 data points, you'll see a slightly better shape. But if you collect 500 data points, you'll see even a better shape, better representation. But if you collect 100,000 points, you're going towards there where what Curie has predicted, the Arena will also predict. But not are you able to follow what I'm saying here? So the more sometimes a distribution fit comes out of your limit on data, how much data you have collected. Maybe what you'll see is the arena is suggesting you to use beta distribution. It's not because it is beta process. It might be an exponential service time, but it is suggesting beta simply because the number of data points weren't enough to capture the whole thing, right? So this is where your knowledge of nature becomes more important. So which one would you choose? If you're talking about like grocery stores, you know it's independent service time. So inter-arrival time distribution. So if Arena says number one beta, number two another Erlang, and number three Poisson, which one would you choose? You're sorry, exponential, because you're talking about time. So you choose exponential, right? Time is a continuous quantity. So we are talking about time continuous quantity. So we are using exponential distribution. So are you able to follow me? You know, and you know the reason why exponential came third. Why exponential came third? Because you did not collect enough data. It kind of points you towards this fact that maybe we should have collected more data. But in reality, you know, this is like kind of in a real project, you would say, okay, maybe I need to collect more data. I need to have few more sessions for data collection. Okay. So this is about nature. I'll tell you one more instance where this nature comes into play. In PERT, you know, I'm switching to project management for a second. In PERT, when you talk about total project time, what distribution were you using there in PERT? What tables were you using? I keep on pushing you into those places, right? Difficult situations. You forgot PERT just now? Have you used a distribution? Have you used a probability table when you're doing PERT? Yeah, so normal distribution you were using, right? But in the individual process there, I don't know if your instructor talked about that. Individual variation in individual task. What was the distribution? Maybe she hasn't talked about that. Was the parameter you're using mu or sigma for an individual task, or were you using A, M, and B? Ah, who said that? Me as a name. See, very good, Asi. You know, I need to clap you for that because I wasn't expecting this to come. So it was beta distribution, right? And the parameters were A, M, and B. So why am I saying this? Because I wanted to tell you something interesting. There's something called a central limit theorem. And it's one of the most beautiful laws that are out there in statistics. Anybody know? I have heard about this term, central limit theorem. Where? In statistics, and you haven't heard that while you were discussing PERT as well? Okay, anyways. So you have a task who's following beta distribution, right? You have another task following beta distribution, another task following beta distribution, but when you sum them up to find the total time, you were using normal distribution. Why? What is going on there? The thing that is happening there is called central limit theorem. Central limit theorem says that irrespective of whatever distributions are happening individually, when you sum them up, some different random variables, the sum always follows normal distribution. So even in simulation, if somehow the processes are adding up somewhere, as in nature, you should know that it has to be normal distribution. I don't know if you're able to understand this or not. Only one. Not very clear. I can feel the lack of confidence in your voice, but it's okay. You just need to know that, you know, when you sum different random variables, the distribution is always normal. Okay. So how do you do that? So this is about nature. We know that by nature, we can argue for exponential, we can argue for Poisson, we can argue for normal and different distributions. But what we do is normally we first of all take the data and plot what is called histogram. At least you should know what histogram is. So you plot histogram, so does it look like a normal distribution? No. right? It's symmetric. Normal is symmetric. So at least you are using exclusion principle. It can be normal. And normally, if you see shape like this, yeah, and this is typically exponential or Poisson behave like that. Okay, so which has a tail, so and so on. So the experts normally go this way. They look at this one and they try to understand the nature, and then they try to fit appropriate functions. Functions means they do it some other way, not through arena. So if it is a continuous one, they have a set of continuous distribution. If it is a discrete one, like Poisson is a discrete one, so they have a set of discrete distribution, and they use different names for it: probability density and probability mass functions. But again, we are not going into too much detail. Sorry, the other way around. Mass function for discrete and density function for continuous data. We have seen examples, so I'll not. This is just an example. So again, some examples here. So there are different distributions available, and we have to pick one. I'm skipping few parts which I don't think are very necessary. So you look at the context, you look at the shape, you look for contender, and you pick. Is it sounding too difficult? A little. But as I told you that we are touching QD a little, but we'll not be handling it this way. We have talked about these already, three. What is the nature behind Poisson? Independent events, times between independent events, distance of process, that is the sum of number of components, normal. We just need to know these three in terms of nature, right? At least you should know these three. Poisson discrete events, time between those events, independent, and if somehow there's some summation going on, you're summing different numbers together, normal random numbers, then always remember that you're thinking about normal distribution. There are more. We just need to know there's a fact that there's if you're thinking of a failure in process, time to failure. Time to failure means like a bulb failing. There is a specific distribution for it, and we call it viable distribution. Okay, and then when you know nothing about it, when you have no idea how a distribution looks like, then you use what is called uniform distribution. Do you know the shape of normal distribution? Sorry? Yeah, it's like a rectangle, right? No, sorry, uniform distribution looks something like this. You just know the limits. Like this is the minimum, this is the maximum. In between, you don't know anything. You say all of them have equal probability. Okay, you understand that? So my question is, if you face a situation where you have absolutely no idea what kind of process is there, but you know at least the minimum and maximum, what would you choose as a distribution? Discrete, if it is a discrete thing, discrete uniform. If it is a continuous process, then you say continuous uniform. Okay, both have equivalent form. Then there is something called triangular. Triangular is it comes when you have one more information beyond that. You still don't know much, but you know the minimum, the maximum, and you know like what is happening more frequently. We use a distribution called triangular. So please, everybody understand that? So just from exam perspective as well, you should be knowing these things. You know this already very well. Independent events, okay? Times between independent events. Sum of a number of different components together. What is the distribution if time to failure is of concern? You'll be using viable. If you know nothing about it, uniform. You just say uniform. Discrete or continuous can be attached to it depending upon what you're modeling. But if you know a little bit more, if you know minimum, maximum, and most likely value, then you use triangular. Beta is what you call a different kind of a distribution. and it's a very flexible distribution. It's hard to explain its nature. More than the nature, it takes any shape. So it's hard to explain its nature like the way we are explaining here. These are designed for something. Beta is not designed for a process, but beta is a general distribution. Okay, people find it that it's a distribution that can fit data very easily, any data of any shape very easily. Okay. Okay, so I think it's getting too difficult now. Parameter fitting. Parameter fitting means you find the value of mu's or sigmas or lambdas. So skip, don't consider this as part of your exam. You don't have to worry about it, okay? So we just need to know we have to fit. But because it's getting too difficult, I'll let you know, as I already mentioned to you before. So the last two slides are not part of your exam, okay? So because there's some math, etc. there, so I'm skipping it. So in Arena, I was hoping that when we reach this point, you already have data and you have laptops with you. Because you haven't collected the data, so we cannot do it right now. But otherwise, what we have done is open Arena, go to tools, and you will see something called an input analyzer. Okay, so you have your data like this. You know, in an Excel file or a Notepad file, it's actually a CS, some file. Even CSV file works well. So you just load it. You say open. You go to that file, load it, and then you will say, it will first give its descriptive statistics, and up there, do you see a fit here? Fit, or there's like fit all possible ones. It's a very simple one. We'll see them more closely. So summary of the best fit. So you see there, it has given you options. It says it seems normal is the best fit, which is giving you the least error. The best second one is beta, Weibull, Erlang, gamma, log normal, triangular, uniform, exponential. So it gives you a lot of options, but you can see that the error is increasing rapidly, except for first three of them. So this is like the best possible fit. And can you read this one? I don't know, it's too small for you. Let me zoom in. No. So normal has two parameters. What are the two parameters? Somebody mentioned that. This is mu, this is sigma. So you note that down. Because next time you'll go to Arena and you want to capture that process, you will enter exactly this line, norm 99.9, 20.1. If instead of that, the best fit would have been exponential, you would have seen here expo with a single value, because it just talks about lambda. Expo 1.5 or something like that, inter-arrival rate, okay? And so on. So this is the fit you need, which you have found using input analyzer. You'll copy this and then you'll put this into your model state when you're going to draw your model in there. Okay, you all understand? So we collected the data, we brought it here, and for each counter or each type of counter, we are going to put data in a single file. We are going to bring it here. It will going to fit, and then it will tell us that this is normal, this is exponential, this is Poisson or whatever. Just one small thing to remember. And it's something that you just need to keep in mind while you're writing the data. If you're trying to fit arrivals, number of people arrived per minute or something like that, Poisson, right? If you write it like this, 1.1%, 3.0, sorry, 1.0, 3.0, because you're thinking it's an integer, right? But if there is like a 0.0 with it, Arena will think it as a continuous quantity, the input analyzer. Make sure that when you're fitting arrivals, there's no like dot here anywhere. It has to be number of people, right? Just a fit. Showing, I'll show you different examples to fit. What I did there, and I can show it to you. I generated this data myself. I know it was generated from a normal distribution. Understand? So I say go fit in the arena and tell me what you found. So this is just to show you can use it as an example where I generated it for normal, I generated it for viable, I generated it for beta, right? I say go take it back to arena, see how good it is able to fit. I know from where it has generated this, right? So this is just an example where I generated this data for normal distribution. That's why you're seeing it like this. But normal, beta, exponential, they are continuous numbers. That's why you see fractions here. Okay. But for if you want to have discrete data, just make sure you don't have any point anywhere in the list. Okay. Because sometimes people have, when they bring this data to Excel, they say convert this to number or something. You know, sometimes Excel put like this 0.0, you save it as a CSV file. You understand what I'm saying? And then it will mislead input analyzer. The input analyzer think that it is a continuous quantity, and it will, instead of giving you Poisson, it will give you exponential. So it may be a problem for you, right? So just taking care of those small things. Okay, so that's it for today. Hopefully you're able to collect this data well and early, so that next week we are able to bring Arena here. I hope that you'll. Today is what? Wednesday. Can you please? I want you to start working on data collection as soon as possible. So is it possible that all of you can send me at least the diagram and identify where you think are the arrivals and something that shows me the whole flow? I think some of you already have that thing, but with the exact numbers. Some of you have given it like an abstract form, like there are some servers. No, we don't need some servers. We need, if there are 5 servers, draw 5 servers. In the conceptual model, but exactly the way you see it there. Because if I recall correctly, some conceptual models roughly represents what's going on. Like if there are like 5 servers, it doesn't say 5 servers, some servers, right? Showing just multiple servers. You understand what I'm saying? So that we can identify, and even if there are 2 kinds in grocery store, I'm sure there are at least 2 kinds of counters, right? They don't have fast checkout counters like 1 to 10 items, something. It's okay if they don't have, they don't have, right? But just make sure that you're not missing anything. In the conceptual model, if there are any such things, make sure it is there, okay? And then hopefully at least maximum by over the weekend, if you could finalize that, and then you can start collecting the data as early as possible, that would be great. But maximum by Wednesday, I want to have Arena here. I want to have Arena where you're doing input analyzer. I want you to be doing the model itself. Okay? Yes. You need to go there and why are you not sure about the number of servers? Okay, so do they vary between 4 and 5, something like that? You're doing which? Oh yes. Can you go there and check? At least, oh, it's still fine. It's fine. You don't have to go there. But whether between 4 and 5, in your diagram keep 5, but will at least identify the points, okay? And if the 5th one is not there, just delete it later, okay? At least you know that these are the 5, whether they are 4 or 5. 5 is the worst situation, right? So we can discuss where are we going to be collecting the data. If one is like if there's an extra server which is not there in reality, then you can just throw it out, okay? No, just draw me the whole thing. 1 queue, then they distribute, right? Yeah, so arrival is already clear from our last discussion, right? And basically server, I just need to make sure that all servers are of same type. If they are the same type, then we'll decide whether we'll be collecting on 2 servers, 3 servers, 4, depending upon how many people you are. Maybe one of you might be collecting the arrivals, and maybe then the rest of you might be like collecting the service times. Okay? Yeah, you'll draw something like this, arrivals, and then a point where, like you say, decide whether it's the people or whoever, someone is deciding. And then you will have like 5. That's the simple model graph. Okay? Why not? Why not? That's I ideally this is what I want. If this is already clear to you, then you can go ahead and collect. But make sure that you collect what we discussed. That's better. Yeah, I don't want you to make collect something wrong and then you have to go back again. Okay. It is just to save your time. Okay. Now, anything else? Yes. Now you mean? Okay. On WhatsApp, you have sent it on WhatsApp? It's okay if I put it up here? Now, what you need is actually, while this flow is just small spelling error, other than that, you need to just draw like what I said to them, the number of counters. Just draw. It is better to draw it as well. Okay. Now for you as well, I think it's in the same place, right? Like if you go to Lulu, there are 2 big sets of counters. In FAM, it is the same. I think it is the same, right? If I've been here for a long time. Do you understand what I'm saying? In Lulu Shaw Hypermart, have you been to Lulu Hypermart? There are 2 big sets. Like there's an escalator in between, and one set here and one set here. Are you following me? Group 1. So if it is not like that, then you can still assume 1 arrival. I don't know how it's happening there. I couldn't recall it. I have been there. I haven't been there for a while. But how is it like a lot of counters there? We have to see how we can capture the arrival. Can we capture them in one place? Can we capture them in? I think for you, because if there are many, you need to keep in mind that people are arriving from different locations. So if there are many counters like this, okay, assume that these are there. People are coming from this side, and this side, right? So we may have to have some reasonable grouping of counters, because this is where they decide one between these. They decide between these. They decide between these. Somehow, you understand what I'm saying? I want you to take a call. Just look at the scenario where it reasonably makes sense. If it is something like this, you have to capture arrival here and here and here. Let's say 3 places. And yes, so the conceptual model should show something like this. exactly what you're doing there, okay? And then within these, because now there are multiple points to capture data, if you don't have any other friends who can volunteer, it's fine. At least have one from each, right? You understand? One of you stand here, stand here. So as a sample, we cannot capture all of them, but at least have them here for an hour or two, and then have them an hour or two, one person standing there. So 2 times for one person. Understand that? So you stand, one person stand here, the other person stand here, the third person stand here, record the arrivals for, let's say, an hour or two. Got that? And then how many of you are there? 5. So 2 of you can already be there capturing. And then maybe a third person can you take a friend with you, or give her a coffee or something, etc. And then you can just do it everything in let's say an hour. You understand the points where I'm asking you to capture? 1, 2, 3, 4, 5, 6. 5 points you have to collect data. 3 arrivals, 3 service. Are you following me or not, brother? Still confusion? Don't understand. Look, people are coming in, right? So this is an arrival point. This is an arrival point. This is an arrival point. Yeah, this is where, this is like vegetable, and a lot of people coming from here. Then some people come from the other side. Some people are coming from somewhere middle in the aisles, right? So you stand somewhere here so that people coming in this direction, you can capture them. This is good. So now you need to have an Excel sheet which says minute, and then you have customers. You need to have a clock in with you. Stopwatch. You say first minute, I start counting people with trolleys actually. Because with a trolley, there might be 2 or 3 people walking together, right? A trolley. And then you say, okay, 5 trolleys passed first minute, 8 trolleys passed second minute, 10 trolleys passed, and then you so on. Okay? Are you thinking about big trolleys and small trolleys? One kind of trolley, or you're considering both types, right? Now it means that you need to have like 2 columns, number of big trolleys and number of small trolleys. And during that minute, you need to count, I saw 3 big trolleys and 4 small trolleys, and so on. Are you being able to follow now? Sorry? I think your situation is already complicated. Let's not make that distinction. Let's assume that they are just counters. Okay, counters here. But at least you are able, let's focus on arrival first. You understand how you're drawing this sheet? Same thing you'll be doing here, same thing you'll be doing here. Same sheet. Yes or no? Okay. Now, while they are going there, this is 3 of you. 1, 2, 3. You have 2 more person. The 4th person, the 5th person, take a friend with you. Give her a good dinner. And then you have another sheet that you'll be drawing. You'll say not minutes, but big trolley, time. Small trolley, time. Which means that when a big trolley comes here, the time taken by that trolley for the checkout. Right? And then if it's a small trolley, and then use your common sense. You cannot differentiate between, with exact number of items. Just see if it's small, if it's big. Just use your judgment, okay? We're not being that precise now. So you say a small trolley. So number 1, number 2, number 3, number 4, number 5, 1, 2, 3, 4, 5, just a serial number. But the main idea is you time, spend on the counter, time. So the same person, these people are doing the same. Is that better now? Now you can do it together, together in the sense that 3 will be doing here and 3 at the same time will be doing it. Or if you can do it, first here and then the same people might be doing it. But I'm saying that it will save your time if you have, like, you take, your younger sisters, the 6th one, and then you just do it for, let's say, 2 hours, the peak time, and you're done with the data collection. Okay? Is that better? Okay. Yes. Just a second. Let me stop recording because it just keeps going.